Welcome to another video. Today we're going to be talking about the distribution function of a random vector characterization. Now, alright, so what is the claim? Well, let x be some random vector with the entries being some random variables x1 to xn. So let it be a random vector. Then the random variables xi, ranging through 1 to n, are independent random variables if and only if it holds that the distribution function of the associated random vector x of some x is equal to the product iterating through 1 to n of fxi, where x is the random variable, of xi, where xi are the entries of the input x, for all such vectors x in the n-dimensional real space. Now, first we shall show that the left to right implication works. So, assuming that these are independent variables, we have that fx of x1 through xn is by definition equal to this identity. So that's the probability of the intersection ranging through 1 to n of the set where we have random variables xi for all I being a subset of the interval negative infinity to xi, where this is the ith entry of the vector x. Right. But these are independent variables. So this means then that this is just equal to the product of the probabilities of the individual sets. And this is equal to the product ranging through 1 to n of the distribution functions associated with the variables x of the entries xi. Right, so this was easy. What about the other one? It is similarly easy. Now, conversely, if this equality holds, so it's denoted by a star. So if star holds, it holds that px is equal to the product measure pxi, like so, to pxn on the class of these intervals. So we have interval from negative infinity to x1, etc., all the way onto the interval from negative infinity, of course open, to xn, where we have x from the n-dimensional real space, and these are the entries of x, right? Okay, but then using the same argument as we have used before, since they are equal on this class, which generates the whole n-dimensional Borel set, using the uniqueness of measure theorem, we have that they are equal on the n-dimensional Borel set. But if they are equal, well, that means then that since the measure is equal to this measure, this satisfies then the definition of random variable independence, which is precisely what we wanted. Thus, the random variables making up the random vector x are mutually independent. Thus, xi for all I up to n are independent or mutually independent if you prefer. And this concludes the proof.